So we have again the same function, the same region. This line is still y equals 3/4 x, but we think in terms of first partitioning y. So that we partition that should be 0 equals y1. Why not? Better repair that. Okay, in any case, we're partitioning from 0 to 3 on the y-axis, so that's less than y1, less than, etc., less than, and I'm going to use the n for y. Okay, so yn is going to equal 3, and we have then our partition of y. We have our typical interval, and we'll call this the, why not the ith? Let's call it j. Jth y interval. Here we're going to have a sample point, and the region of our triangle is going to run between these two lines. Now the length of that interval is going to depend on our sample point in our typical jth interval. Okay, so the sample point is going to be the sample y value is going to be y sub j star, and for that particular interval we partition our x interval. Now the x interval is going to go from here to here. It's not going to go from 0 to anything because there's no triangle from 0 up to this point. We don't intersect the triangle until we get to this point, so the question is, what is our x interval? What's the x interval corresponding to our jth y interval? Well, that's not too hard to determine. Y equals 3/4 x. So when y equals y sub j star, x equals what? Well, x, solve for x, we get x equals 4/3 y. Takes the value 4/3 y sub j star. So we partition the interval from 4/3, from where I'm standing it looks a whole lot like a 7, 4/3 y sub j star to 4. So now our partition for x is 4/3 y sub j star less than x, less than 4, or less than or equal to x less than or equal to 4. So our partition is going to be 4/3 yj star, and I've got a less than sign again. Okay, repaired that. 4/3 yj star equals x naught less than x1 less than, and so forth, less than. Now I used n for y, and don't think I've used that n anyplace else, and I've decided that I really want to use m for y. So we're going to have an xn which equals 4. Now our delta Vij is still going to be f of xi star yj star delta x delta y, so that our sum is going to look a whole lot like it did before. However, our volume is going to be the sum from j equals 1 to m of the sum from I equals 1 to n, and n is going to be different when we consider different y increments. We're going to be partitioning strips of different length down here. So our xn is actually going to be an xn of I. And our sum is going to go from I equals 1 to n of j, and that's not n of I, that's n of j. And that's not right either. No, actually I'll take that, that's right. So we go from I equals 1 to n of j, some number of intervals, it depends on which y interval we're partitioning to start with, and that's then going to be a sum of f of xi star yj star delta x delta y, and that's going to approach the integral of f of x y dx dy. Now we have to integrate x first because our limits on x depend on which partition of the j interval, which subinterval in our partition of the j interval we're considering. So our x partition went from 4/3 yj star to 4. Again, our xi's and our yj's are now squeezed down to x's and y's basically, and our integral then will go from 4/3 y to 4. Our x interval goes from 4/3 y to 4. Our y interval goes from 0 to 3, our original y interval. So we have two expressions for the volume, two different integrals that should give us the volume. We have this integral, and I don't have room in this sheet to write out the x over 4 plus y over 2 plus 3, but that's going to be the same here as it is here. But our limits look different. In this case, with the y integral going first, our y values go from 0 to 3/4 x. And our x values then go from 0 to 4. In this case, our x values go from 4/3 y to 4, our y values from 0 to 3. Both sets of limits accurately describe our region. In this case, our description of the region could be written as 0 less than or equal to x less than or equal to 4, and then for y we have 0 less than or equal to y for a given value of x. Y goes only up to 3/4 x. So that would correspond to this picture of the partition, or this picture of the interval. And this leads us again to an integral from 0 to 3/4 x of our function with respect to y, and then from 0 to 4 with respect to x. In this case, we regard the region as 0 less than or equal to y less than or equal to 3, and for any given y value, x goes from 4/3 y to 4. So we have 4/3 y less than or equal to x less than or equal to 4, and this gives us an integral of an integral from 4/3 y to 4 of our function with respect to x, and from 0 to 3 with respect to y. We can generalize this procedure to one where x is bounded above and perhaps below by two different functions and exists over some interval of x. We can reverse the order of integration by reversing the roles of x and y. Y equals 3/4 x, for example, can be solved to give us x equals 4/3 y, which we use in this form of the integral. In this form we use the 3/4 x. So we have a definition of our y in terms of x. We can of course solve that then for x in terms of y and use whichever one gives us the more elegant picture.